Okay, let me start it. Okay, this presentation is visible. Okay.
Yes.
Thank you everyone for joining with us. Today I will present the robust filtering schemes for machine learning system, which will defend the adversarial attack. So first, let's see what are the adversarial attack. So see this image here. This image will be classified by state-of-the-art machine learning algorithm as a dog, and you will see it's actually snow image. Just this hill area, there is a shadow of the dog, which will made it classify as a dog. This is one of the example of how adversarial image actually work. Which is like to ask a one thing, but for the machine learning algorithm, it is completely different thing. So from the NIST definition, adversarial attack can be defined as manipulation of training data, machine learning model architecture, or manipulate testing data in a way that will result in wrong output from ML. So from this definition, we can classify adversarial attack in three types. One is poisoning attack, which is manipulate the training data. Another is evasion attack, which manipulate the input data, what happened in the runtime or deployed time. Another is Trojan AI, where a backdoor was created in a machine learning model, which just activated when the specific input was given. In this presentation, I will only only explain about the evasion attack and Trojan AI. When I will mention the adversarial attack, it will be actually only meaning the evasion-based attack, not the poisoning attack. So see some of the example. It is the most common example that a stop sign only just few noise could be detected as a green light by machine learning algorithms. Another example is just put a special type of sunglass can face recognition can detect as a different person. In more subtle noise can be given on the medical images, where benign medical image will change to a malignant by just adding a noise. This noise will be multiplied by 0.04 and which will be very small. So type of there is an adversarial attack, like this is a score based attack. Only 1 point change classify this dog to cat. It is named 1 pixel attack. There is some patch attack as well as where putting this patch sticker changes the classifier to banana to a different to a banana to toaster. And another attack where this putting these things make machine learning algorithm to not classify this as a persons. So there are other based attack like gradient attack and decision attack and adaptive attack which works on the defense. I will mention the gradient attack and decision attack later. So gradient attacks are like that it works on the loss function and it add some noise based on that to change the classification. Here this fish adding some small noise, it will change to cat. This example we can see that here this goldfish and here is the noise level, it will started to change to a different class, starfish. Another type of attack is the boundary-based attack, where a bank of noise was given. This attack is mostly for the black box machine learning model. Here, a bank of noise was trying to change the image to different thing, but it still remain it as a class which was its initially was. And this attack is actually very effective. And let's say the Trojan AI. So suppose we have a neural architecture in a model. There is a Trojan model or parameter was set in a way that for a specific input, it will change the output class. It is also a one type of machine learning, one type of adversarial attack. It's slightly different from the adversarial attack because it's not adding anything in the input. It is working on the model. So defensive strategies for adversarial which are currently common is one is the adversarial training. It trains the data set with the adversarial example. One of the limitation is it actually reducing the machine learning model accuracy, and also it can't be employed in the deployed system. It needs to be done in the training phase. And generating the adversarial example also troublesome work because there is a different types of attacks and new attacks are coming every day and we can't train the model every time a new attack is come. Another process is input reconstruction or transformation. Changing the input in a squeezing, the method resizing is actually work better or do multiple image for a class, that also work as a defense. But limitation is it's a vulnerable to the adaptive attack. If the attacker know the what type of defense is used, he can bypass that by working on a query-based method based on that defense. Another is the model modification, change some of the architecture which will be specified for the adversarial attack, but limitation of it is in that it need to change the architecture on the model in the deployed system, so it's a limited applicability. We can't use that in everywhere. Uh, so let's see what are the adversarial attacks as some of the limitation also. We did an extensive study on adversarial attack, how they perform in the physical world. So here we can see that we have a different type of adversarial attack. What we did is we printed those in our paper, and we see that they still act as adversarial or not. It was very interesting to see that most of the adversarial attack, which are very famous, like Carlini, Wagner, or Deepful, they don't perform when you printed them. Uh, and also there's the environmental factor as well, such as we did some of the image resized and back the size again, then those not working rate also get increased. We rotated some image, then also they are not working as adversarial. We create a motion effect by blurring the image, then it was also kind of completely diminish all of the CW and full attack effectivity rate. And we also there's a illumination which is the increase in the brightness of the image, and printed that out. That also destroyed the adversarial effectivity of those things. Here I was showed that the resize scale and back the scale, here the degree of the rotation, and here the blurriness level, and here's the brightness level. The reason behind this is that um, our physical data, the when it is formatted in the digital format, it converted to an integer. It converted to the floating value, and if the noise was added in the floating value, and when it return back to the printing, as the color format is the integer, this noise can't come back. It's also similar for the sound and web and other approaches. So the problem is that noise needed to be at a higher level so that when it converted to a physical format, it is still exists. So from our mathematical analysis, we found that for 8-bit single channel color, the minimum noise have to be 0.0019. Here n is the bit color. However, this experiment has a limitation because we saw that if we printed in a different type of printer, as printer actually follow a different color format, so there is some limitation of this experiment. Someone can say that our motion and illumination was not actually real life motion as we simulated it, but other researcher recently confirmed this experiment, and their result actually align with our experiment. And it was seen that based on the whatever the printer is, the destruction rate for default CW close to the 100. And I didn't see any of the 1 pixel attacks survive after printed them in a print form. So let's see the problem on the deployed system attacks. Let's see the first is a physical world problem. Physical world is like my face is the input data. It is in the physical world, and I can modify. I can wear a sunglass. I can put a sticker on my face, which can misinterpret the machine learning model. And second is the input sensors, which will take the data. CC-cam could be an input sensor. And in the first layer, in the input sensor, there can be some modification could be done. Like there is an attack of adversarial patch where a camera lens, a sticker was put on the camera lens, and it classify image differently. This is one type of can happen. Also, the changing the framework, changing the firmware, or configure something in that sensor system can create the adversarial attack. It is one of the attack point. Second attack point is when the sensor is going taking the data, converting the data to digital format, and then sending it to the model. It is going to a communication channel. In this channel, someone can modify that, and this is the only way that higher lower part of base attack can work, because here the data is already converted in the binary and the floating point, so there is no environmental factor like as brightness or rotation. Those are not working in here. And then, but however, I think this communication channel security is not up to the ML ops. And the second layer is on the operating system is in the place. And now you can say that here can the attacker can change the data before sending it to the ML model. But what we can argue that if the attacker can change the data in here, he doesn't need to add the noise here. He can change the full input because it is not visible by the human or anyone. And he actually effectively actually controlling the full system in this place. He can control the output as well. And the fifth, when the change architecture ML model is changed, it is the kind of the tricky one because we need to verify the outputs are consistent with the other outputs came before. This could be the one of the way it could be a tricky things. And the last on the output medium is like printer or some kind of control who's taking the decision based on the ML output. There could be some kind of attack, but I also think this will goes outside our purview. In this presentation, I will mostly focus on the attacks which happen in the physical world and which can consistence of the ML model. So these are proposed solution. We will check the input and we will add a input filter which will diffuse the evasion-based most of the attack. And when the output will come, we will check the output filter will check the consistency of those output as the before output to find out there is any Trojan AI was involved or not. Here I am showing the different adversary attack types of the evasion-based attacks. This is a very generalized form. It is not actually represents, but it is a good to that there is a differentiate between those attack types. Like in the FGSM attack, in the upper I just simulated it, and the lower is the actual FGSM. In all of the FGSM image, we can see the scattered noise, which is a different color level. In JSMA, there will be a added perturbation around the actual object. In CW, there's some missing bit or some added bit, which is very hard to distinguish. And diffull is more advanced. Only 1 or 2 pixel has been changed to change that change the output. This actually gives us an overview that different attack works in a different way. So what we did was, if we applied a filters, it will change the image, and if we differentiate it, we can find out those changes. So like if we run a smoothing algorithm, which can remove the noise, we get a new image. If we subtract this image from the previous image, we'll only get the noise. And the noise between the clean image and the process image will have a significant differences if we check the histogram averages. And this difference can be used to classify them. One is adversarial and one is not adversarial. So what in our model actually does, we take the clean image set, we run some of the filters, check the differences image, and take the image properties like as mean value of the histogram and signal to noise ratio. And for the adversarial image set, we also take those value and we create a rule-based method that if the histogram mean and SNL value is in that level, they will be classified as an adversarial image. If not, they will classify as a clean image. So here is one of the sample. It's converted to histogram. Adversarial image is converted in this way, and clean image has a less noise. If we did a color map, it is more evident, and we can do take the signal to noise ratio by Fourier transform, and we can see that there is a difference of the adversarial image and the clean image. So we did at least 100 of the filters, and we take all of their histogram value, and based on that difference, we try to classify them. We can see that CW2 has actually no effect of this, but we also showed that CW has a diminishing rate when it comes to physical example, and we actually work on the physical example, but it is actually work very well against the other attack types. So this is one of the example we showed. Here we done the adaptive smoothing, and here we take the differential image. We can see that clean image differential image has very distinguishing between the other types, and deep full HCW actually can't be differentiate much, but it is see that FGSM and GSM can easily detect by adaptive smoothing. By adding additive noise, it is very easy to detect CW2, but not a JSMA attack. So different filter actually works better for different attack type. So we test with the gradient-based attack and decision-based attack, and we use 6 type of filter. I classify them by using 6 type, which is noise reduction, sharpening, thickening, shrinking, noise addition like blurriness, additive noise, dithering, transform to transform the Fourier, Laplace, or Laplace, and texture-based Gavot, sensors, edge detection, Sobel, Kenny, analytical distance, and more. If we can see that here the same noise addition and noise cancelling filter work for those 4 type of attacks which are actually from the same attack family, and those are not work well with the deep full and hop skip jump, but the texture based filters actually work with the good with the decision based attacks family, but it's not as well as with the gradient attack. Also, if we take the best performing filter for one attack type and apply it to the other attack type, we can see the best attack type in the FGSM quite well work with the other attack type, but not with the different family. And it is actually goes same in the other way also. So based on that, we can see that we need a multiple class family, and that will be work better. So in our experimental setup, we took different types of attack and do the more differential based on their category they formed. And we use dataset mainly MST, CFR, ImageNet, and the attacks was formed using ResNet and a VGG model, and also some of use the CNN. And we used only 2 metrics, signal to noise ratio and histogram average. Initially, we used some other metrics like local binary pattern and other different filter metrics, but we later see that those actually very much correlated with SNR and histogram average, so it was not required. So if we can see that like Gaussian smoothing, additive noise works better for MPGT based attack, sharpening blur works for ImageNet FGSM attack, and different type of combination works for different types of attack. But if we wanted to find those which sequence was best for which type of attack, the total search space is actually immense. For only 50 filter, it will have a huge search, and it will be very tough to do that doing a random or a brute force search. So that's why genetic algorithm comes in the play. We used a genetic algorithm method, and if we say that randomly search, it will take sometime we get 80% accuracy, somewhere before between 80% accuracy, but running genetic algorithm after 20 iteration, we got a close to 90%, more than 90% accuracy filter. This experience was done for only 6 filters. And if we do the brute force attack where the 8 filter and we try to suppose search the 5 best filter which has an accuracy over 85%, we can see the genetic algorithm search less than others. It is only search a few, and it can get at least 10 number of 10 sequence which has a performance better than 85%, where a brute force search is so huge that we can't able to experiment it for when the filter size is 17. And random search also getting higher as we increasing the filter size. So that's actually gives the idea that using genetic search is a better for this problem. So what we does it, we use a genetic algorithm, and it was working, it was focusing on accuracy and time at stake and the diversity of the family. Because as we see it earlier, that if there is a diverse family, it will be work from diverse filter family, it will be work for different type of attacks. So our phenotypes are actually filter sequence, filter 2, filter 6, filter 7, and we calculated each individual accuracy based on their detection rate, based on their time consumption, the time has come, and how many filter family was represented in the sequence. It was counted as the diversity level. Based on that, we actually use a multi-objective fitness. We used a utility strategy, and our was terminated when we get a best fitness which was not changed after a certain time. So in the it will work as a way that input data will be come and a set of filter sequence will be selected, and based on that we'll detect that it is adversarial or not. So this is actually the overview of the how algorithms work. Filters are going here. GA population was generated by random, and we are checking based on the accuracy, diversity, and time course. Fitness is calculating, and if the sequence list was not effective with the threshold, we are doing crossover mutation, and I initiated drop operation to maintain the diversity. I will explain that later, and then the new population was actually generated. Okay, so this is the one explain. We did a variable length. This is the phenotype, and we can see that if we change the order, time actually change good. So even for the same order, accuracy will be same, but time consumption rate will be changed. So time is the needed. Here are the filter family sequence. This 3 means these 4 was come from 3 different filter family. 1 means these 2 comes from 1 filter family. More the diverse is this, it has a more chance to go work against the unforeseen attacks. And the diverseness we have to tackle, there is a 2 type of diverseness. One is the insider diverseness, which is that if these filters are all from same family or not from same family. And as we are giving a dynamic option to select one of the sequence from a set of the sequence, so that set need to be also diverse. So we can't put say a similar sequences. So that is the set diversity. So we have to work with the 2 different type of diversity, and that's why I initiated a drop off operation. When the genetic algorithm first started to work and reached a certain accuracy, I pull off the best performing filters as a pool and remove the most common filters from the population. Then it drop the accuracy for a certain time, but it is, again started to climb. And when it reach a certain point, I again do the same operation. I take the best performing sequences and most common filters from there. So the F5 and F11 was not present in this sequence, and here F4 and F1 was not selected in this sequence. So there is a 3 different pool was collected, and every time we give one from each of the pool for the input filter detection. So this is actually genetic performance rate. We can see the accuracy got rising. The time was fast. The different time was fast is fluctuated, but little time started to reduce. And here we show the average accuracy and the best accuracy, as we need a multiple sequence. So average accuracy was also needed to see. Best accuracy climbed very fast, but average accuracy of the full population set needed time to take climb up. So experimental result will give that this sequence is the filter number 8, 14, 19 has a good F1 score, and diversity was also good, but some of them was the diversity was not good, and we will pick based on this. And this is the Pareto font presentation. We presented as a black are the diversity levels. Accuracy was presented in blue, and filter family diversity was in time was in this side. These greens are actually the Pareto optimal set of my genetic algorithm, and I actually targeting this to use in my sequence. But limitation of this input filter is that I need to generate adversarial inputs for taking these filters, and I need to access the clean training data so I can find out that what are the threshold of the noise value. And this method is not actually effective against the Trojan AI and backdoors. And we can say it's dynamic, but it's not adaptive, because filters number are finite. An adaptive attacker can run thousands of query and he can find out what are the defense strategy and he have to overcome. And this system is not actually automated, so it is not good applicable for a deployed ML system. So to remove those limitations, we worked on the output filtering script, and we think we need an adaptive defense strategy which don't modify the learning model and don't require the adversarial knowledge. To do this, we converted this full problem as an outlier detection problem, where we only work on the clean data. We will assume that we don't know any knowledge about how adversarial inputs works. We will only have the knowledge of the clean inputs. So here I represented a MNC dataset using TSNE to visualize how they are placed in the 2D representation space. So you can see that all of the digit has a place and it is clustered when they are clean. When I added 40,000 adversarial sample from 3 different attack set, we can see that this cluster was very much unrecognizable and kind of unseparable of those clusters, and there are a lot of overlap. But this will remove if I use only my SNR and histogram based value to cluster. Here you can see that blues are actually the clean data. This is FGSM attack. This is JSMA, sorry, this is CW, and this is a JSMA attack. So it is very visible that if I work with the histogram and SNR value, applying 14 best performing filters, I did my empirical study, they are actually very separable. And if I only take the clean and adversarial, mean combining all three adaptive similar, this is also very good separation. So for outlier data, so we are assuming that we only have the knowledge of this clean data. We don't have any knowledge of those. So we did a one class classification technique, and we pick negative selection algorithm. Negative selection algorithm, to simplest term, suppose you are classify a classification technique where you will classify the dog, but to classify the dog, you will check your input data except everything which are not dog. And if it match with anything else, it is not a dog. It works in that way. And it will generate the data which are not dog, and you will only match with that. It was the simplest way to put the negative selection algorithm. And there is a variation of negative selection algorithm, which is V-detector negative selection algorithm. My supervisor invented this algorithm a few years back, and we are working it. And it's very interesting, and it faster than negative selection algorithm and a process because it using the variable size detector, which was previously mostly used the constant size detector. And there was an algorithm was given. It is just said that it generates the negative samples in a defined variable size. And as negative selection is a random nonlinear, and the variable size also made it unpredictable for an attacker also. And this negative selection algorithm was very good to use in the password authentication system also, which was another interesting one. So what I did is that I take every class level like dog, cat, car, and for each class level, I generated a feature mapping where I take where I generated the negative detector set for them. And so I for more the classes, I have a more I have defined negative detectors for different classes. And in the runtime, it is working as like that input data is coming from the ML model. I'm getting the output level. And as I have the output level and the input data, I'm checking they are fall in the negative detector for the negative detector. If level is 1, I'm checking with the negative detectors for level 1. Is it an outlier or not outlier? If it is a outlier, I am saying stopping it as it's a there is a possible Trojan AI or it's a misclassification, and if it's not, it's going to the output. So why this is what you will understand in this flow diagram. So input is coming to the ML model, and initially NSA detector is not working. It is going directly to the output, and NSA detector is get trained from the clean data set. So ML model output and going to the clean data set with the input, and clean data set is generating the NSA detector. initially. And when the answer detector was generated, it started to check that the new inputs are getting by detector or not. And every time a new inputs are detected as a clean, it was again changing the NSA detector. So there is a consistency with the ML model and the NSA detector. So we can say there is a cold start problem, as initially NSA detector has not enough data, but we can say that if we put clean data first as a test program, NSA detector will get to know this, and this will then NSA detector can automatically update itself as the user are using the ML model. So for example, experimental result, here we show the different attack types and the accuracy of the MST class of 0, 1, 2, 3, and CFR airplane and CFR dog. I didn't able to do the CFR, CW, and default because they actually don't exist in the physical example from my experience. And here is the confusion matrix for all of the digit. And here all three types of attack, FGSM, GSM, and default was used. And we can see that we have accuracy of 95, 96% of the accuracy. If we remove the CW attack, the accuracy will be actually close to 100%. So other than negative selection algorithm, we explore different one-class classification technique as well. There are different classification like linear model, one-class support vector machine, proximity-based HB, also histogram-based outlier score, subspace outlier detection, probabilistic method, COPD, fast COPD, they are also good. Outlier ensemble method are most popular, like isolation forest or feature bagging, and neural network based outlier detection model, which works for one class classifications, are autoencoder, variable autoencoder, and also a GAN based model that are also worked. I also explored those model, and these are the result between V detector and those model. We can see some of those method works actually better than V detector. Like LSCP, it has a very good performance, but it fluctuates some, but which V detector is more consistent. I was surprised to see that autoencoder based and GAN based method didn't work well. I think it could be the configuration problem that we run. We had the low iteration rate, or it is the data set needed to be more, other problem could be happen. But I think the work, the V detector is sufficient. And but still we suggested that we could use the KNN a feature bagging LSCP V detector together and dynamically pick one of them as a model. So this is the basic workflow of our dual filtering scheme. But the ML model will get the input data and it will train the outlier, and the more the input data will come, it is started to train it more. And we get an adaptive attack detection module, which will detect that inputs are coming as very similar or not, because that is a sign of the query-based adaptive attack. However, the patient adaptive attacker can avoid this module, but that will be computationally very expensive. And also the adversary attack are transferable. So it is kind of hard to control the adaptive attacker in this way, but what we can say that we made the adaptive attacker works harder than before. And the traditional attacks like backpass differential approximation based adaptive attack will not work in here because our negative detector is changing every time. But if someone devices adaptive attack based on our target, that could work, but will be computationally very expensive. So this is the detailed components of my dual filtering scheme. For the inputted scheme, it is a more design which we actually practically implemented. And we can see that here as the negative detector was trained, here the genetic algorithm was trained in the normal data set was actually updating every time. Adversarial data set also updating in the real time, and new filters was generating, and detector was also changed. So the system was very dynamic and adaptive as it learned in the runtime. And we see that it is more effective than the current defense systems, which has a limited applicability. So in comparison with our other framework, our framework actually works quite well than other methods. And More than that, we have some advantage as our method can start without adversarial attack set. Our outlier detector will detect the adversarial attack, and then based on that, it will revise the filters. So we have that in common. None of those attacks are actually effective against the Trojan AI. Our methods are actually effective, and we don't need to change any architecture of the ML model. We are completely considering the ML model as a black box model. And we don't need the adversarial training, so no reduction of the ML model accuracy also. And our model is not an ensemble method, which is computationally expensive. So that's also a good point for our model. And the summary of full work is that we use a multi-object genetic algorithm, which has a variable length to search the set of filters that will be effective against different type of AS. We devise an adaptive negative filtering methodology to detect adversarial attack that does not modify the ML model or information about the ML model. Our strategy can be implemented in any ML-based system without expensive retraining. We said any ML-based system as because we are completely considering our research on the input, not on the anything from inside the ML model. So it will be same for all ML system. And current adaptive patterns which are proposed last few years, these are ineffective as we are changing our negative filter detector set, and we are also checking the query-based attack. And further source will be need to conduct more experiment, as my total experiment was more of a on the computer vision domain. I did some of the testing with the sound adversarial attack on the audio domain with Fourier transform. That also works good, but I think there is a need a more extensive study on other domains. So, okay. We did some of the publication. There is a patent already submitted in here. The 3 conference publication was already done. Three journal paper was submitted. One will be published very soon, I hope. And the mathematical formulation of the genetic algorithm, fitness function, and penalty function, weight, all are details in those paper. If you are interested, these are available in my ResearchGate and GitHub. You can see that. And I give the references here, and if you have any questions, you can do that.
Okay, Kishor, thank you so much for an interesting talk. Okay, now is the time folks in the cyberspace to if they have any question to ask. Any question? While everyone else is thinking about asking a question, let me ask a couple of questions from you, Kishor. One is, this application is for offline, right?
No, online. I mean, it is a deployed system.
Oh, okay. But then you have GA in the loop, but GA usually has been used for offline.
Okay, so online, when it is detecting an adversarial and clean, it will be added in the dataset. And from the dataset, time to time, it will retrain the genetic algorithm. It will redo the genetic algorithm for new filter search.
So when you're doing the genetic algorithm, you're offline.
No, we are in online, but it is happening because the new data has come. So there will be new search. And this will be added as a plugin before the machine learning model, around the machine learning model, and they will retain it after a certain numbers of input count. In the beginning, there is no data in the adversarial dataset, so genetic algorithm will not work. But as the negative selection algorithm and outlier detection will started to generate the adversarial attack set, the genetic filter sequence list started to be populated.
I see. Okay, thank you. Can we go back to slide number 24, 25?
Okay.
Yeah, this one. Yeah, 24 is good. Let's go to 25. Yeah.
Yeah.
Okay, when you are dropping, once it reach to this level, to certain level, you are taking that one off and then you're starting again, right?
Yes.
Okay, how do you know that you're reaching to this point? And then why don't you use niching to basically detect all the pick that you have within this experiment?
Actually, I had to tackle two problems in here. I need a different, I need a filter set which are unique to each other and a set which has no common between themselves. And I tried to do other diversity technique and those became so complex, and that was I didn't. And about that, when the average sequence, so best sequence or reaching the accuracy of 1, then I am actually started to take them off. So here its accuracy actually reached the 90, above 99%. So I am taking the best 4 samples as a pool 1 and remove the most common filters from all the population. So that's why I can keep a pool diversity. So if I take 3 sequence from these 3 pool, I will not get a common variation.
Okay. Okay. Thank you. What about 26? Can we go to 26?
Yes.
The curve with orange, that is the one by your method, right? By GA?
Below or this figure 15 or 16?
Figure either one, 15. Let's look at 15 more specific.
Yeah, 15 is the accuracy actually. I did explain is the F1 score.
Yeah.
And blue one is the time consumption.
Okay. 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 Thank you. I think it's more clear. Okay. Is there any question from Kishore on cyberspace?
Yes, I have some questions.
Yes, please.
So can you go to slide number 21?
Sorry. Actually, I think I hide the 21 slide. You are talking about 20 or 22?
The genetic algorithm where you have the filters.
This one?
No,
This one?
Oh, I see the 21 that you have the
FT1,
filters.
FT2, like
Yeah.
the filters.
Yeah, it is in our presentation. Somehow, we don't have it.
Can you go to the next one from these? The next one, yeah. Next one.
Yeah.
This one?
Not that one. Before that, I think 4
Okay,
slides
I
before
think
that.
I understand that what happened. Okay, let me go again.
Okay, it's okay. I can ask without that slide. So the question is, like you are using multiple filters to be able to detect different types of attack, right?
Yes.
So each filter try to detect certain type of attack. So my first question is, why is it important to put the filters in some specific sequence? What is the reason behind that?
Time consumption. Because more, let's say that, let's see that FT8, filter 8, I have 100 test image. FT8 can detect 99 of them. So time consumption will be less. But if FT8 was behind the last and FT3 was the come, then and FT3 can do only 50 image, then I have to push all of them together. So the best, the reordering those sequence actually gives a less time.
Okay, so during test time, you don't need to use all the filters to detect the attack. As far as you get enough
Yes.
accuracy,
Yes.
you can leave.
The rest of them I can leave. Yes.
Okay.
I think this was actually better explainable here. Like say that here the same sequence, just the reordering them, reducing the time.
So what is your threshold like to decide whether that is good enough or not before using?
The fitness. I had a fitness function which is, if this is a certain threshold, I am counting that is a good. And that was also weighted, and it's using some that if accuracy is over 90% and the time consuming was less than the other average time consuming consume, that is the good enough. And uh, there is one thing that we did a penalty function implementation, which I didn't describe here, that actually reduce the fitness function if the length is too long.
Okay. So my second question is, like, now you are using, like, you use some well-known filters like Sobel filter, those kind of filter
Yes.
to detect the attack. How about learning those filters? Like, as you know,
Using a neural network or
neural network.
autoencoders.
Yeah.
Yes, that's what I was actually initially doing. I thought that neural network can teach me these filters. Why I need to do the well-known filters? But here I didn't show that experiment result. But the thing is, when I use the autoencoder and getting the kernel, which I essentially actually filters, they are very much optimized for that data set. Like what I got from the MST set, if I got a sequence from MST set like FT2 and FT3 is a good, that sequence actually works for other MST variation like FMNST, Fashion MNST or EMNST, and even some extent to CFA dataset that works. But what filter I got from the autoencoder, that is only work for the MST dataset. So yes, those has a better accuracy rate and they are very easy to generate, but they are not transferable. And what I see that adversarial attacks are transferable. If you so why not my defense will be transferable? That was my perspective, and I wanted to make a more broader sense. So I found that this filter sequence they works a more than certain accuracy in all of data, but autoencoder based filters which I got they don't work that extent.
So don't you think, like, given enough amount of data for the autoencoder method?
That could be reason. I think if I do more experiment, it would be better. But it is also that if more data I give that, it will be more generalized for that specific data set. I mean, in simple term, what I will get from autoencoder using MNST dataset, I may not use that for FNMST or EMNST. But this common dataset, a filter can be used.
Okay, all right. Thank you.
Okay, any other question from cyberspace?
I have one question. First of all, thank you, Mr. Kishor Datta, for your nice presentation.
Thank you.
I have a question like how you make sure your NSA detector is not overfitted as you train your NSA detector only the clean data set.
That's a good question. We didn't actually test that it was overfitted or not. We experiment with 40,000 adversarial image from MST and 20,000. It works well, but yes, thank you for the suggestion. We didn't test that it get overfitted or not. We probably need to do outside testing also.
Yeah, because as that your data set is clean, that means there is not that much variation in your data set, if I'm not making a mistake.
Yes,
So,
that's actually valid point. Currently, we employed in a real system where we are checking the medical CT scan and MRI images, and we think we could find that it is overfitted. And also to be noted that negative selection algorithm is not actually using alone. It was actually using ensembling with the other outlier detection models such as LSCP and feature picking and isolation forest in a dynamic time. 2-3 of them was picked.
I have one more question. Do you think that there are some data augmentation technique like mosaic augmentation or blurring and mixing of images? Do you think that this kind of data augmentation technique could be the alternative solution of this kind of adversarial attack?
Yes, that's actually what I mentioned in the very beginning of the slide. If you see, okay, in physical world, if we just reducing the features image size and then again size it back, the adversarial effect gone. So what you said, yes, there's a very effectively work. But
Okay.
there are some attack types which it doesn't work, like CW or deepful. But again, those attacks actually not exist in the physical world.
All right. Thank you. Thank you so much for the answer.
Okay, any other? You have time for one more question. One more question. Okay. If not, I'm going to thank Kishor, and then I also like to make an announcement. Traditionally in summer, we're going to let all the students to give most of the presentation for the